I'm not sure you guys heard this at home. Strong bases are never leaving groups in SN2, SN1, E1, and E2. So if you need an OH to be a leaving group, you've got to do something too. You either have to protonate it, which means you got to have strong acid around, or you have to turn it into a tosylate or a chloride. And that's, I guess, another just basic principle to write down and commit. You know, kind of every reaction. Let me write it down. Never have enough space. All right, you're never going to see a reaction where you have a strong acid in the mechanism and a strong base. Right? If I take sodium hydroxide pellets and I just dump it into concentrated sulfuric acid, it's a bad idea to do. Has anybody done that? They don't let you guys play around nearly as much as. So really, to do stuff like that, you need to go to work. You're not going to do that in a teaching lab. I should probably stop the recording. But if you're just sitting around in the lab, you're waiting on stuff to happen. There's nobody watching you. You can do this. Anyway, it generates a lot of heat. Like sodium hydroxide pellets straight into sulfuric acid. It instantly boils whatever water's there, and it splatters all over the place. Like it splatters this strongly acidic basic stuff. It's really dangerous to do that. So don't do this in a mechanism, right? You're not going to have a chemical reaction happen that's got both a strong acid and a strong base in the mechanism. If you had that, right, they would just react with each other, and now you're going to have weak acids and weak bases. And nothing else will happen. So you can kind of, as a general rule, right, if you're under acidic conditions, if the reaction's being run under acidic conditions, you can have protonated oxygens, because that's a strong acid. So to generate that, you have to have strong acids around. You can have a mechanism that might have an O- like this, right? That's a strong base. You can have that if it's under basic conditions. But if you're running a reaction in sulfuric acid, you're not going to have something like this formed. And if you're running a reaction in hydroxide or lithium amide, you're not going to have something like this formed. Like right now, like there's only a handful of mechanisms for you to know. And I know it seems like a lot, but those kind of general rules, we don't want you memorizing mechanisms. Some of you, and everybody differs. Everybody's got a different, things that stick in your mind, your memory, differ between people. All of us have different abilities to memorize stuff. So some of you in here probably can maybe memorize everything on this exam. Maybe. But if we're getting to the point where no one's going to be able to do that. Exam 3 is certainly there, and if you manage to memorize your way through Orgo 1, Orgo 2 is going to be a bad time. Right? So Orgo 2 is a lot more reactions, a lot more mechanisms. So it's better if you can start to learn kind of the fundamentals of how a mechanism works. Make sense? Okay, so let's do another fun reaction. Give me the product of that reaction. What kind of reaction is this?
What temperature is that? Does it even matter?
Doesn't matter.
What's the leaving group?
Aha. Is there a leaving group?
It's an acid.
It's acid base. So there is no leaving group. Yeah, methoxide actually, and there's a whole lot of Orgo-2 going on in this reaction, right? So you guys are probably getting sick of this. These are like trailers, right? Teasing you for next semester. There's no leaving group. So OCH3 minus can't be a leaving group in an SN2 reaction. And even if it was, what would be the nucleophile in this reaction? Right, yeah. So, right, it would be like my stupid reaction over there. So methoxide would just come in, and I'm going to tell you this again. I'm not trying to confuse anybody. Don't worry about this. This actually happens a little bit. Methoxide will come in and attack this carbon, and you'll kick out methoxide, and you can see it. We'll see it next semester. This was an acid-base problem. Similar. There was a similar acid on your acid-base worksheet. So why are CHs? Those of you who were at the review session last night, we talked about this some, so you've heard this. But generally, you should probably assume CHs are not acidic. The vast majority of CH, the protons on carbons, are not going to be acidic. But you have seen, right? You've seen protons on carbons be acidic in this class in the E1 and E2 elimination. Okay, so I keep wanting to erase with my phone. All right, so, right, in the E1 reaction, so we have this positive carbon here. That positive carbon is really strongly electron withdrawing, right? It wants electrons to neutralize that positive charge. The carbon doesn't have a full octet. Atoms really want full octets. So having something really electron withdrawing there tends to make things around it more acidic. The electrons in this CH bond interact there and make that H a lot more acidic. So you get, that's a proton on a carbon rendered more acidic because there's something electron withdrawing next to it. The same is going to be true for even the E2 reaction, right? So we've got this, and I know everybody loves me talking about antibonding orbitals. We've got this antibonding orbital there that electrons can go into. The CH electrons overlap here, and that lets you do this anti-elimination, right? So, but this is a much weaker effect. Trying to put electrons into this antibonding orbital is a much weaker effect than having a carbon without a full octet. And so in E1, we can use a weak base, water, ethanol, whatever. Right, so this carbocation makes that H so acidic, water can pull it off. Over here, in E2, we need a strong base because that chloride, right, that chloride's electron withdrawing, it's pulling electrons toward it, but not nearly as strongly as a carbon that doesn't have a full octet. Okay? All right. So, in this molecule, the same thing is happening, right? The electrons in this CH are interacting with that pi antibonding orbital, and if we pull this proton off, we end up with we end up with a molecule that looks like a negative carbon, and actually is. It's got a decent amount of negative carbon character to it. But that and so normally, like I said, a negative carbon is going to be really unstable. And it's not like this molecule is super stable, Right? This molecule is a way stronger base than hydroxide. But it's stable enough to form. Whereas like imagine pulling a proton off of hexane, there is no base that will do that. Here we can. The carbonyl's pulling electron density toward it, the carbon's partial positive, the oxygen's obviously electronegative. And so that makes the H's on the position bonded to the carbonyl relatively acidic for a CH. In this case, you got two carbonyls. Right? So the first thing that happens is acid base. All right, not first thing, this is what happens. All right, and the product then I'm going to draw this out. Still one H there. Humans see faces and things, so maybe that looks like the molecule sticking its tongue out at you or something. I don't know. Okay. Draw a resonance structure of that molecule. Draw two resonance structures for the molecule I just drew, the product here. So like I said, you can delocalize this negative charge onto both oxygens. So the blue arrows give the blue resonance structure, the red arrows give the red one. You can move those electrons, that lone pair delocalizes over both oxygens and the carbon in the middle. Right, that's actually a pretty stable, that is a relatively stable anion. So, like on the acid-base worksheet, you had to use an amidine base. So the base, it wasn't as clear as a methoxide, right? It was an amidine base, and a lot of people chose to deprotonate the NH. And again, all things being equal, if you're going to deprotonate an NH versus a CH, that's a good bet. But you have to look at where the delocalization ends up. And then you also have to look at the base. The trouble on the worksheet is these neutral carbonyl oxygens are only going to be, they're really weak bases. They are basic, but they're not strong bases, so they're not going to pull an NH off. Questions about this so far? I'm going to do one last bit here. I'm going to erase my resonance structures. All right. So give me the product of these two reactions together. question, so there was a sorry to interrupt you while you're working. There was a question about the temperature of that first step that I talked about. You asked what the temperature was. So you don't need to know it to figure out acid base. Acid base reactions generally are not greatly affected by the temperature. But they tend to be pretty fast. Like if they're favorable, they're favorable. And so we tend to run them either at room temperature or even cold. Sometimes they're really exothermic. So if you're going from a super strong base to a relatively weak base, you'll actually cool that reaction because it's so exothermic. Like you don't want other stuff. Most of the time the molecules aren't as simple as these, right? There's all these other, if you look at modern medicinal chemistry, you've got these very large, complicated molecules. There's almost certainly going to be these other functional groups that can do chemistry. Right? So you don't want to just maybe the reaction would go faster at 120 degrees, but I don't want to do that because if I do that, the rest of my molecule is going to fall apart. So a lot of times an acid-base reaction will cool it down to minus 78 or so and try to let it go a little slow. Acid-base tends to be fast enough, you don't need to worry about how long that's going to take. Okay, so step one, you guys know the product at step one. Let me get rid of these excess arrows here. And on a reaction like this is really sort of what am I trying to say? I have no idea where that thought was going. All right, you've got step one. So now step two is just going to be to treat product of step one with these molecules. So do you have a leaving group? You do. Do you have a nucleophile? What is the nucleophile? Nope. Yeah. So once you do this reaction, that's your nucleophile, right? It's an anion. It can be an electron donor. So, actually, an important point. We talked about this some last night too. Molar equivalents matter here. You should generally assume a 1-to-1 molar equivalent. Like if I put this reaction up, I say I've got this thing and I've got sodium methoxide and methanol. You're going to have a lot of methanol. There's always going to be a lot of solvent around. You should assume you've got 1 molar equivalent of sodium methoxide. So 1 mole of that, 1 mole of this. 37 millimole of that, 37 millimole of that. There's a problem in in the substitution worksheet that it says 2 equivalents. That means you've got 2 molar equivalents, right? So whatever is here is 1 equivalent. This thing would be 2. So if this is 1, this is 0.3 mole. This would be 0.6 mole, right? So assume 1-to-1. So we're assuming here all the methoxide turns into this anion. All right, so you're definitely right. If there were 5 equivalents of methoxide, just imagine, I used 5 molar equivalents of methoxide, I'd get this anion and I'd have 4 moles of methoxide left. And then methoxide's going to be a nucleophile and a base. Okay, but we don't have that. So we have this thing. So we got a leaving group, we got a nucleophile. So which kind of reaction is it? The folks who said E2, why E2?
Because it's high temperature.
Temperature. So absolutely. 100 degrees suggests elimination. Why is it not elimination? There's no beta hydrogen. It's a trick. All right, so the alpha carbon has the bromide. There's only 1 beta carbon, and it has no proton. Right? So there's no way to make a double bond between the alpha and beta carbon. There's no beta hydrogen to abstract. So if your thought process got you to elimination here, you got a base, you got a leaving group, and it's 100 degrees. E2 is a if there were a beta hydrogen, this would be an elimination. All right, so the product is going to be SN2. I'll go ahead and draw that. There you go. So that's the SN2 product, and it's SN2 this substrate, the benzyl bromide there can only do SN2. If we did this exact same reaction, but instead had this, right? So if that red bromide, it looks like a really subtle change, right? We went from a primary to a secondary bromide. That will slow SN2 considerably. But the more important thing is now you've got beta hydrogens. So this reaction here would give us styrene. You don't have to know that that's styrene. You get an alkene. Styrene is a carbon-carbon double bond bonded to a benzene ring.